Okay, so we're back. We're looking at periodic trends of different atoms and their electron configuration similarities. Hydrogen, lithium, sodium, potassium. Those are all atoms that you're going to find, or elements that you're going to find in the very first row of the periodic table. Okay, so this brings back our discussion of the S block, the P block, the D block, and so on. All of these atoms are going to have their valence electrons in the S block. And since they're in the first row, they're only going to have one valence electron in that s block. Okay, so if you think about hydrogen, hydrogen only has one valence electron. Its one valence electron is in that 1s orbital. Lithium, that one valence is in the 2s orbital. Sodium is in the 3s. Potassium is in the 4s. Okay, so metals like these, they tend to lose one electron. Okay, so if you think about lithium, if lithium loses one electron, now all of a sudden its valence electron is, or its valence shell is the 1s orbital, which is filled. So it has the same electron configuration as helium. We'll get into those in just a little bit more in a second. Now, electron configuration of cations. Okay, so this compares the sodium cation, calcium, the calcium cation. Sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. Now, sodium generally forms that plus one cation. Okay, so that means it loses an electron. It becomes oxidized. The electron configuration for the sodium cation, well, it's going to be that electron removed. So an electron configuration of 1s2, 2s2, 2p6 is going to be it. Calcium. Well, calcium has a full 4s, but let's look at that. Calcium is going to become oxidized to form the Ca2 plus cation. It's going to lose two electrons. It's going to lose those two valence electrons in the 4s orbital. And so there is the electron configuration for a calcium cation. Now, you'll see those same sorts of trends based on similarities in the rows in the periodic table. So if you look at fluorine, chlorine, bromine, and iodine, these are all halogens. They are all in the same column in the periodic table. Note the similarities between their valence or their outermost electrons. They are all a p orbital. They all have 5 electrons in those p orbitals. The n value changes, but that orbital remains the same, or that subshell remains the same. It's the p subshell, or that p orbital, that double dumbbell shape. There are 5 electrons in there. And so generally what that means is these nonmetals, these are examples of nonmetals, they tend to gain an electron in order to attain a stable electron configuration. So fluorine, for instance, will gain one electron, and now all of a sudden has the same electron configuration as a noble gas. It has a 2s, 2p6 electron configuration like neon. We're going to see that in just a second. Now, electron configurations of anions. Chlorine forms the chloride anion. Well, chlorine has a 3s2, 3p5. Those are the valence electrons. When it gains an electron, so it's the Cl minus, that chloride ion, now all of a sudden it's got a 3s2, 3p6 electron configuration. Okay, now the transition metals, that central block of the periodic table, makes things a little bit complicated, but really it's kind of knowing a trend and you'll be in good shape. Okay, so if we take iron versus the iron 2 plus ion or the iron 3 plus ion, okay, the electron configurations for these vary a little bit. Iron has an electron configuration of 4s2, 3d6. Those 4s2 electrons are the farthest out. Then you've got those 3d electrons there that you have to deal with. Okay, so now when you look at that 4s2 electron configuration, that 4s2, 3d6, the first two electrons that are going to be lost and cause this to become oxidized are those that are the farthest out. So these are going to go. In which case, now we've got Fe2+, where the outermost electrons are the d orbital electrons. So 3d losing, we're going from a +2 to a +3, we're losing one of these 3d electrons to become 3d5. Now, lots of people have a question as to, why basically. Well, the reason for that is when you think about the d orbital, that's that double dumbbell shape. That double dumbbell shape can be contorted in three-dimensional space to make up 5 different configurations. So that looks a little bit like this: 1, 2, 3, 4, 5. Okay, so think back to whenever we drew the energy diagram. We wanted to place all of our electrons based on Hund's rule. We wanted to maximize electrons with the exact same spin. That gave us our lowest energy level. So with this d orbital, there are 5 different positions. Each one of these can hold 2 electrons. The d orbital can hold a maximum of 10 electrons. I'm going to fill in the first 5 electrons. Okay, so there's 5 electrons. Now our 6th electron in this 3d orbital is going to be facing downward. Okay, now if you think back to Hund's rule, or the Pauli exclusion principle. The Pauli exclusion principle, we've got opposite spins. Okay, so this right here is not a problem with respect to the Pauli exclusion principle. Now, we can get to a lower energy level, well, by simply removing an electron. When we remove that electron, now all of a sudden, we've got our 3D 5 electron configuration. We lost basically our 6th electron there. Okay, so what that means is the first 2 electrons, the outermost electrons, those are lost because they were way the heck out there. They were in the 4s orbital. Now, that next electron, the 3d6, that 6th electron, the reason that we lost that was because we reached a stable configuration of our electrons whenever we put 1 electron in each one of these 5 different positions and gave them identical spins. Okay, so this 6th one was just kind of like, it was there, but it really wasn't bringing anything good to the party. Okay, now our filled shells and half-filled shells are the most stable electron configuration. So these right here are half-filled shells. If we can have 5 filled shells or 5 half-filled shells, that's better than 4 half-filled shells and 1 fully filled shell, as would be the case with a 3d6 configuration. Now the next thing is core notation. That brings up basically the similarity between all of our atoms. The core notation or core electron configuration accentuates the core electrons, those which ones are on the interior, and the valence electrons. Okay, iodine, for instance, has this electron configuration. Now, the core configuration for iodine is basically 1s2 all the way to 4p6. If you look at that 4s2, if you highlight, I'm going to highlight or underline 4s2, 4p6. Well, that electron configuration is the same as that of krypton. So this right here is the same as writing bracketed Kr, because this is basically the electronic makeup of krypton, and anything that follows that 5s2, 4d10, 5p5 is unique to iodine. So core electron configuration, or your core notation, is where you find the nearest preceding noble gas. In this case, we found krypton, and you put that in brackets, and then you fill in the valence electrons. So you basically have a core plus valence electrons. So the valence electrons for iodine are 5s2, 4d10, 5p5. Now must be a noble gas that you put in there. The last thing that I wanted to talk about is kind of definitions. So electronic properties, basically paramagnetism. So whether or not something is going to be attracted to an electronic magnetic field is based on whether or not it has unpaired electrons. So if an element or a species has unpaired electrons, and it is attracted to an electronic or a magnetic field, it is considered to be paramagnetic. Now, diamagnetic is the tendency of a species not to be attracted or to be slightly repelled by a magnetic field as a result of electrons being paired. So pairing of electrons, it's going to likely be repelled or only slightly attracted to a magnetic field. Paramagnetic is when you have unpaired electrons, and that's going to be attracted to an external magnetic field. All right, I hope this is helpful. This actually wraps up chapter number 6, so have a great afternoon.